Now, let me introduce you to the first two probability rules that you're going to see in this class. We have more coming up, but for now, we're only going to focus on the addition rule and the complement rule. Let's start with the addition rule. Before we read this, let me emphasize something here. The addition rule is going to be used when you're finding the probability of A or B. So that should be the first remark that you make. Now, let's go ahead and read this. If A and B are two events defined in a sample space, then the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. If I'm finding the probability of A or B, it makes sense to say, let's take the probability of A. This is take the number of ways A can happen divided by the total outcomes in the sample space, plus the probability of B, which is the number of ways B can happen out of the total number of outcomes we have in the sample space. So that part makes sense, right? Because we're saying probability of A or B. Well, let's find the probability of A. Let's find the probability of B. Let's go ahead and add those. But then here, why are we subtracting? Maybe this is the part that doesn't make sense. Why are we subtracting the probability of A and B? Without looking at an example, how can I explain this? Well, let me just keep it simple. To find the probability of A, you have to count the number of ways A can happen. To find the probability of B, you have to count the number of ways B can happen. It could be the case that you double count it. You're going to see how we double count in some cases. And so that is why we're saying, go ahead and subtract the probability of A and B. Or else, you're double counting. Once we look at an example, I'm going to show you how this double counting happens. Now, another thing that I'm going to mention here is that if two events are mutually exclusive events are events that cannot happen at the same time. So if you know that two events cannot happen at the same time, then the probability of A and B is equal to 0. So what's going to happen to our addition rule if we have two mutually exclusive events? Well, we're just going to come here and we're going to say, look, I found the P of A and B is equal to 0. So here I'm just subtracting by 0. In that case, we would just have the probability of A or B is equal to the probability of A plus the probability of B. Even if we have mutually exclusive events, we're still using the same formula. Here, I just want you to recognize that if A and B cannot happen together, if they're mutually exclusive events, then the last part of our formula, the probability of A and B is just going to be 0. Now, let's go ahead and talk about the complement rule. The complement rule is going to involve the complement of A, which is denoted using this symbol here. This means the complement of A. The complement represents everything that is not in A. Thus, we have the formula here below. The probability of A plus the probability of the complement of A is equal to 1. We can go ahead and rearrange this equation. For example, we can say, why don't we solve for P of A? What is P of A equal to? If I want to solve for P of A, I would go ahead and subtract by the probability of the complement of A. And I would do this to both sides. Why are we subtracting by the probability of the complement of A? Well, because we want to leave P of A by itself. So here on the left, if I subtract by the probability of the complement of A, I'm going to be able to cancel this sum by P of the complement of A. If I go ahead and do that, we're going to have P of A by itself on one side. On the right-hand side, we're going to have 1 minus the probability of the complement of A. Okay. We could also take this formula and solve for the probability of the complement of A. In that case, we would need to subtract by P of A on both sides. Again, why? Because we want P of the complement of A to be by itself here on the left-hand side. So that is why I'm subtracting by the probability of A. Once we do that to both sides of the equation, we're going to have the probability of the complement of A by itself on the left-hand side. On the right-hand side, we're going to have 1 minus the probability of A. We're now going to look at a set of questions where you have to use probability rules to compute probabilities. From this exercise, we're going to be asking ourselves for probabilities of selecting a card from a fair well shuffled deck of 52 cards. Here we have the deck. Notice we have 4 different figures. We have the clubs, the spades, hearts, and diamonds. We have 13 cards for each figure. For example, we have a ace of diamonds, a 2 of diamonds, a 3, a 4, 5, 6, 7, 8, 9, 10 of diamonds. Then we have the jack of diamonds, the queen of diamonds, and the king of diamonds. It is going to be the same case for each figure. Another thing to note is that we have 4 cards with the same number or face. Again, we're going to be calculating probabilities. We're going to be asking ourselves, what is the probability of selecting a card with a certain characteristic? Now, let's go ahead and compute probabilities. For the first 2 questions, we're going to be calculating the probability by taking the number of outcomes in the event space divided by the number of outcomes in the sample space. Let's consider part A. What is the probability of selecting a card that is a face card? Let's write P of face, which stands for the probability of selecting a card that is a face card. So how many outcomes do we have in the event space? Here's how you can think of it. The event space contains the set of all the cards that have a face. That is all the jacks, all the queens, and all the kings. How many do you have in total? Well, you have 12 face cards. That means that you have 12 outcomes in the event space. Now let me erase here. Now, how many outcomes do you have in the sample space? In the sample space, you should have all the possible outcomes of selecting a card from this deck. So your sample space here is all of the cards. That is 52 outcomes. The probability of selecting a face card is 12 out of 52. Go ahead and enter this on your calculator and round to 4 decimal places. You should be getting 0.2308. So again, here we simply took the number of outcomes in the event space divided by the number of outcomes in the sample space. Now, would you be able to compute the probability of selecting a card that is a black? So here I'm going to write P of black, meaning the probability of selecting a black card. For this probability, you simply need to think of the number of outcomes in the event space. How many black cards do you have? Here you have all the outcomes in the event space. These are all the black cards. We have a total of 26 black cards. So the numerator here is going to be 26. Now, what is the sample space? The sample space is all the possible outcomes of selecting a card from this deck. Here we have 52 possible outcomes. So go ahead and take 26 divided by 52. You should be getting 0.5. Let's consider problems where you have to use the addition rule. That is, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. In part C, you're being asked to find the probability of selecting a card that is a face card or a black card. Notice we see the or word. When we see or, we should be thinking about the addition rule. Here I'm telling you that I'm going to give you problems where you have to use the addition rule. But if I didn't tell you what rule you needed to use, you would know that you need to use the addition rule because it says the probability of selecting a face card or a black card. So make a note to yourself. The hard part of computing probabilities is knowing what probability rule to use. Here I'm going to write the probability of face or black. According to the addition rule, we need to take the probability of getting a face card plus the probability of getting a black card minus the probability of getting a card minus the probability of a face and black. Let's start by computing the probability of selecting a face card. This is a probability that we computed earlier. We said we have 12 cards that have a face. So we're going to take 12 divided by 52. We have 52 cards in the sample space. Now, same thing with black. This is a probability that we computed before. We have 26 black cards, and we're going to divide by 52, which is the total number of outcomes in the sample space. Notice here, we're using the addition rule, but in order to calculate the probabilities, we still need to think of taking the number of outcomes in the event space divided by the number of outcomes in the samples. Now, let me go ahead and highlight what we did. We looked We were looking at all the face cards. I'm just going to circle them here. We were also looking at all the black cards. We counted 12 face cards and we counted 26 black cards. Earlier, I mentioned that when we're calculating the probability of A or B, there is times where we count outcomes twice. And that is the case here. When you were counting the face cards, you counted some of these cards twice. When you were counting the black cards, you included all the face cards that had a black figure. When you counted the face cards, you counted those cards again. For that reason, the addition rule says, go ahead and subtract the probability of A and B. In our case, we have face and black. Here on the numerator, we're going to count the number of cards that are black and have a face on it. Here we have 6 cards, the jacks, the queens, and the kings of clubs and spades. Again, we have 6 cards that are black and have a face on it. The sample space here is still 52, which is the total number of outcomes. So notice, by doing this, we're making sure that those 6 cards are not being counted twice. Now they're only going to be counted. Go ahead and enter this expression into the calculator. You can go ahead and enter the expression that we have here, or you could also do the sum of this work without using a calculator. Here we have a common denominator, so we can simply take 12 plus 26 minus 6, that is 32 out of 52. Go ahead and round to 4 decimal places. You should be getting 0.6154. Now I'm going to let you do the example here below. You're going to find the probability of selecting a card that is a hard card or a black card. Notice here we see the word or. We know that we need to use the addition rule. The last 3 examples here are going to be examples where you could use the complement rule. You don't have to, but you could use it. In part E, we have what is the probability of selecting a card that is not a face card. To compute this probability, you could count the number of cards that don't have a face on them. We have 40 cards, and divide this number by the total number of cards. Or you can think of the total number of cards we have in the sample space, which is 52. That will give you your answer. That is one way that you can do this. I'm going to call that method number 1. Now, on method number 2, we're going to consider using the complement rule. We're going to say the probability of selecting a card that does not have a face is equal to 1 minus the probability of selecting a face card. We already know what the probability of selecting a face card is. We computed this probability earlier. So it's going to be easy for us to say, let's take 1 minus the probability of selecting a face card, which is equal to 12 divided by 50. Notice here I'm simply writing 1 minus the probability of selecting a face card. The probability of selecting a face card is 12 divided by 52. If we round to 4 decimal places, we get 0.7692. If you take 40 divided by 52, you should also get 0.7692. Again, I told you that I was going to show you examples where you could use the complement rule. You don't have to, but you could use it. Here, what I used was the probability of the complement of A is equal to 1 minus the probability of A. Here, A is the event of selecting a face card. The complement is the event of selecting a card that does not have a face. Now, what is the probability of selecting a card that is not a queen? I'm going to let you do this on your own. However, I want you to go ahead and use the complement rule. Here, we want to find the probability of selecting a card that is not a queen. So I'm just going to write the probability of not queen. The probability of not queen is equal to 1 minus the probability of queen. Again, the probability of the complement of A is equal to 1 minus the probability of A. Is the event of selecting a queen. The complement is the event of selecting a card that is not a queen. So think about this on your own. I will ask you to enter your answer below. Make sure to round to 4 decimal places. Now we have one more problem. I added this problem because I want to show you how sometimes using the complement rule can help you work faster. Using the complement rule might require you to count less. In this problem, you're being asked to find the probability of selecting at least a 5. So here we want a card that has a 5, a 6, a 7, 8, 9, 10, a jack, a queen, a king, and then we're assuming that the ace is the highest card, so we also want that card. So when it says at least 5, that means 5 or more. Here I'm going to write 5 or higher. That is what we're wanting. Here I copy the deck of cards above so we can see them. If I want to calculate the probability of 5 or higher, I can go and count the number of cards that have a 5 or a higher number divided by the total number of outcomes, which is 52. So that is one way you can do it. So again, I want to emphasize that it is possible to do it another way. We don't have to use the complement rule, but we are going to use the complement rule. Here, the probability of 5 or higher is 1 minus the probability of 4 or lower. Here I'm going to highlight all the outcomes for 5 or higher. We're also going to include all the ace cards. And so those are all the outcomes where we have a 5 or higher. Now the complement of that is 4 or lower. Here you have an example where you're going to count less if you use the complement rule. The probability of 4 or lower is how many cards do we have that are lower than a 5? Well, we have a total of 12 cards, so that is 12, divided by the total cards in the sample space, which is 50. Again, here you have an example where if you use the complement rule, you have to count less. Here, we only have to count 12 cards. These are the cards with a 4 or a value lower than. If you enter this expression in your calculator, you should be getting 0.7692. So here's the last remark I'm going to make. If you're finding a probability and you're having a hard time counting the possible outcomes in the event space, and if you're wasting a lot of time trying to come up with the list of all those outcomes, then think about the complement. It might be easier to count the outcomes of the complement of A instead of counting the outcomes of A. Okay, so that is going to be the remark that I make. Most of the cases, when we find ourselves having a hard time counting the number of events we have in the event space, we go ahead and think about the complement.